Welcome to all. Myself Dipti Ranjan Patnaik and I am working as an assistant professor in GL Bajaj Institute of Technology and Management, Greater Noida. Today's topic is digital modulation technique. So, this modulation technique is one of the, or we can say, this is the vital process in any communication system, because we have to transmit the signal from a transmitter to a receiver which is far distance, which is established, or which is uh, established in the at the receiver end, which is far from transmitter. So, modulation is nothing but the processing, this is the process of converting the electronic signal to in such a form to another form, that is we can change the characteristics of this the carrier signal, that is what the characteristics belongs to, that is amplitude, phase and frequency of the transmitted signal. So, this is the definition, that is modulation refers to the process of converting electronic signal from one form to another, such as changing the amplitude, phase and frequency of the transmitted signal. So, in digital communication, the modulating wave, that is modulating wave is nothing but your message signal, consists of binary data, but in case of analog communication system, this modulating signal was a continuous signal, but here the modulating signal is a binary data or an MRE data. Binary data means it's having a 1 0 form, 2 bits only, and in MRE form it includes m number of bits, encoded version of it, and the carrier is your sinusoidal, which was also sinusoidal in case of analog communication system. So, in other words, digital modulation is the process of encoding digital information. So, we are encoding the digital information, that is nothing but the your binary data into the amplitude, phase and frequency of the transmitted signal. So, we will see what is happening in the if I will change the amplitude according to amplitude, what will happen, according to phase what will happen, according to frequency what will happen. So, digital modulation is a scheme in which the baseband information has first been converted to digital message. So, in general our baseband information is in the form of analog form, that is why we have to change the baseband information, that is baseband is nothing but your message. Okay. This message should be converted to digital form, that is a message that assumes only one of finite number of discrete values, finite at a time. So, at a time there is only one value. Okay. So, this is before modulation takes place. So, before modulation process we have to change the continuous baseband signal to a digital message. Okay. This is the first step. Here in place of modulation, the term keying, that means switching, is used. So, in analog communication system, in analog modulation system, we are using the term modulation, that is simple modulation technique, but in case of digital modulation scheme, in case of in this case we are using the term keying instead of modulation, that means that keying is nothing but the switching, that switching from one form to another form. So, in general modulation techniques combine numerous bits. The modulation technique, what it does, it combines numerous bits into a single symbol, and the rate at which the symbols are transferred determines the transmitted signal's bandwidth. This is the these are the main important aspects of any modulation scheme. Similarly, techniques for digital modulation might be linear or non-linear. So, in linear modulation scheme, the transmitted signals amplitude and or phase vary linearly. So, in linear modulation your amplitude and phase changes linearly with digital modulating signal, whereas in non-linear modulation scheme the transmitted signal's amplitude remains constant. Okay. We will see what will happen in the next slide. So, we will now classify the digital modulation schemes according to the changing of your amplitude, frequency and phase. So, different types of shift keying methods are there. So, these shift keying methods in digital communication are amplitude shift keying. If I will focus on amplitude, changing the amplitude, if I will focus the frequency, changing the frequency, then it would be frequency shift keying, and if I will focus on phase, then it would be phase shift keying. So, next in amplitude, first I will say the amplitude shift keying. This class is for amplitude shift keying. So, your in amplitude shift keying, amplitude of the carrier is switched from one value to another depending on the modulating digital input. So, your definition is modulation. What is modulation again? The changing of the characteristic of the carrier signal with respect to message signal. So, our amplitude of the carrier signal is changing, that is switching or keying from one value to another depending on the modulating signal, that is your message signal. In other words, amplitude of the sinusoidal carrier is changed from one to another according to digital message signal following AM principle, same, that is amplitude modulation principle. The encoding technique has an impact on the bandwidth of the transmitted signal as well as your robustness against impairments. So, the encoding techniques, that is modulation technique, has an impact on how we are selecting the modulation technique. We are assuming these techniques based on the bandwidth and the robustness against the impairments like fading and intersymbol interference. That the fading is nothing but the power loss of the signal, as these signals are coming from long distance and they are they are coming from striking to buildings and many more trees. That is why the signal strength is very low at the receiver. So, they are facing the problem fading and also the intersymbol interference. So, many symbols are coming. So, it would be interference between them, that is why these are the problems are there. So, to overcome these problems, we have to select appropriate modulation schemes. So, the simplest digital modulation approach is your amplitude shift keying, or it is often called as on off keying. Okay. So, there is only one unit energy carrier in this approach and it is turned on or off depending on the input binary sequence. Okay. So, one unit energy carrier in this approach is used and it is turned on or off depending on the input binary sequence. What it wants to tell, actually this is the form, this is your carrier signal and this is your carrier signal and this B is nothing but your message signal. There is in the form of 0 1 0 1, that is the form, and it is, if 0 is there, then our carrier is now 0. If the message symbol is 1, then carrier has the same frequency and phase. Similarly, if 0 is there, then your amplitude will be 0, and if 1 is there, again it will copy this, and if there is 0, then it would be again 0. So, this is the ASK output. Now, this is the binary ASK transmitter. So, as we are using only the simplest ASK is nothing but the binary ASK. So, we are using the binary form, that is binary data sequence is inputted towards the one encoder which is on off level, which has on off level, and it will generate the binary data. Okay. So, then it will pass through a product modulator and then it will multiply by a basis function which is already we have read in Gram-Schmidt orthonormalization process, that is this is one K-rate signal. Okay. So, here is your message signal, here you have K-rate signal. So, now it would be product this product modulator will be product this signal, multiply these two signals, and the binary ASK signal we will get at the output. This is the simplest version, that is we will get. So, the if 0 is there, then that would be 0 energy, if 1 is there, that would be a root EB energy, and this is the product modulator. Okay. And our carrier is your phi 1 t, that is root over 2 by TB cos 2 pi FCT. If I will multiply this, then I will get the ASK output waveform as S of t equal to same root 2 by TB cos 2 pi FCT multiplied by 0, if I will send 0, and if 2 by 2 TB cos 2 pi FCT into root EB, if I will send the symbol 1. So, in ASK, when the symbol 1 and 0 are given to the product modulator, the output is defined as, I have already told, that is S1 t equal to your root 2 EB by TB cos 2 pi FCT, and S2 t would be your 0. So, if 1 is transmitted, that is S1 t, if 0 is transmitted, that is S2 t. So, your t has a limitation is 0 to TB, time bound is 0 to TB. So, where EB is the transmitted signal energy per bit, that EB is nothing but your transmitted signal energy per bit. Now, S of t is nothing but the, we have already known the S of t is nothing but the your A cos omega c t. If I will find out the EB, what is the energy associated with the bit, then I can find out by integrating this S of t square. Energy I can find out anything, energy is if x of t is given, then I can find out the energy as a integration 0 to that time period and x square t dt. So, here S of t, that is S of t whole square dt. So, 0 to TB, your S of t is nothing but the A cos omega c t, that would be A square cos square omega c t dt, and I can write like this. So, cos square theta is nothing but the 1 plus cos 2 theta by 2, cos square theta equal to 1 plus cos 2 theta divided by 2. So, I can write like this, cos square theta 1 plus cos 2 omega c t dt divided by your 2, then A square by 2 I can split this, this is a 1 dt, then A square by 2 0 to TB cos 2 omega c t dt. So, A square by 2 TB, then plus A square by 2 your cos 2 omega c t dt, nothing but the A square sin 2 multiply 2 pi f t divided by 4 pi f 0 to TB, and as we know the sine function, it would be 0 in the per cycle. That is why I will get EB equal to A square by 2 into TB. If I want A, what is the value of A? That would be A equal to root 2 EB divided by TB, that is the your amplitude. So, here only one basis function phi 1 of t, because we have only a symbol 1 is there, and 0 for 0 it is 0, and is given by phi 1 t equal to root 2 by TB cos 2 pi FCT, and your S1 t, your S1 t equal to 2 EB by TB cos 2 pi FCT. If I will write in terms of phi 1 t, I can write, if I can write that root EB multiply root 2 by TB cos something. Okay. Then it would be root EB, if this one is your phi 1 of t. Okay. Now, S2 t equal to your 0, because we have only phi 1 t. Okay. Now, ASK system has a signal space with one dimension. So, this is only one dimension signal space. It has two message points that have the coordinate points as follows in one dimension, but two coordinate message points. So, I can find out the message point SSS11. If I will find out the S11 as S1 that is 1 1 means that is your message S1 and your basis function phi 1 of t dt. So, I will integrate this 0 to Tb and I will get this 0 to Tb S1 t I know root 2 Eb divided Tb cos 2 pi fct. Similarly, phi 1 t I know this much. Okay. So, again integrate, I will integrate 0 to Tb 2 by Tb, I will multiply this to root 2 by Tb root 2 Tb, that is 2 by Tb multiplied by root Eb, then it would be your cos square 2 pi fct dt. Similarly, 2 root Eb by Tb, this would be your, and 0 to Tb cos square theta equal 1 plus cos 2 theta by 2, and it would be what will happen, it would be if 1 is there, that would be t integration of 1 dt and cos 2 theta by 2 is sin 2 theta by 2 theta, that is it would be again it would be the 0 as a for one cycle. So, it would be what will happen, root Eb divided by Tb multiplied by t Tb 0. So, it would be, this would be only Tb. So, Tb will cancel and root Eb. Similarly, S21 is nothing but your 0 to Tb S2t phi 1 t dt. So, your S2t, you already know that your S2t is 0. So, it would be your 0. So, this is the point, one message point is 1 here root Eb and another message 1 is your 0, and I have the threshold point or decision boundary is middle of this 0 and Tb, that is root Eb by 2. This is also known as decision boundary. This is region 1 and this is region 2. If any signal is coming in this point, then it would be assumed that this is point 1 message 1 bit 1, and if any point is coming in this region, then it would be message 0. So, I can analyze this signal space in terms of also Gaussian wave. So, here this is the Gaussian wave for 0 symbol bit, and this is the 0 sorry for 1 bit. So, this is also decision boundary. If any term is coming in this region, then this would be considered 0, and if this is coming this region, it would be considered as 0. That is the message S1t is located at S11 and S2t is located at S21. So, region Z1 is corresponding to message 1, your 0 corresponding to message 1, and region Z2 is corresponding to message 0. Now, root Eb is the distance between the two message points. This is the distance is your total distance is root Eb. Now, we can find out the what is the error performance or probability of error if I will send 0, if I am getting 1, or if I am sending 1, what if I will get 0, what is the probability of getting this error. So, the probability of error P is an important performance metric for comparing digital modulation techniques. Incorrect detected decisions are called as symbol error. If I will get incorrect data, then it is known as symbol error. So, this is the transmitted signal, this is the channel, this is the your channel, and transmitter, while transmitting the signal, it is the noise is added at the receiver, and the receiver signal is your x of t equal to SIT plus W of t, and then it will be multiplied with the product modulator, or we have already seen 2 times, and then it will pass through an integrator, and then it will pass through a sample circuit. So, it will sample at every Tb, then I will get here, I will get the x1 and I will compare this through a threshold level root Eb by 2, that is your threshold, that is root Eb. If greater than x of t greater than Eb by 2, I will consider root Eb, that is consider 1. If less than, then I will consider it as a 0. So, the received signal x of t in the presence of additive white Gaussian noise with the assumption that symbol 1 or S12 is transmitted, that is x of t equal to your S1t plus Wt. We know that x1t I can find out x1 is nothing but from x of t multiplied by phi 1t dt. So, your x of t is nothing but your S1t plus W 5 I can split like this, then I will get S1t 5 that I can write S11. Similarly, this one is a W1, right? That is nothing but I know S1 equal to root EB plus W1. Similarly, assume that W1 is the Gaussian, that is W1 is a Gaussian with 0 mean and n naught by 2 variance. Since W1 is Gaussian, the observation y is also Gaussian. Now, so we are making decision with respect to y. To do so, we have to write PDF of y. To write PDF of y, we have to find the mean and variance. So, what is the mean of x1? That is mean of S1 plus W1. S1 mean is nothing but your root EB, and W1 is only W1 mean is your 0. So, we get root EB as a mean. The similar variance is nothing but variance of S1 plus variance of W1. So, variance of S1 is nothing but 0 and variance of W1 is nothing but your n naught by 2, that is sigma square. So, when symbol 0 is transmitted, the likelihood function is your Fy. I am finding transmitting 0. What is the likelihood function? That is, this is the Gaussian function, that is 1 by pi n naught divided, because sigma square is your n naught by 2, n naught by 2 2 will be cancelled out, e to the minus your a 0, this is 0, that is y square by n naught. Similarly, when symbol 1 is transmitted, the likelihood function is your same here, instead of x mu is your root EB. So, the probability of error when symbol 0 is sent, and I will get detected as 1, that is probability 0 is nothing but the root EB by 2 to infinite. Okay. This is the root EB by 2 to infinite, this region. I will integrate this Fy of y of 0 dy, and I will put this Fy here, and I will, after some calculation, I will find out this one. And how I will solve this? We know that our error function is this one. So, let z equal to this much and y equal to how much? This much, and dy is dz root n naught. So, p of n naught equal to nothing but the 1 by pi n naught root pi n naught, and e to minus z square root n naught dz, and the limits will be, if y equal to root e by 2, then z root n naught equal to root e by 2. So, if z equal to only z equal to this much. When y equal to infinite, it would be z equal to infinite. So, our limits will be changed to half root e by n naught to infinite, half multiplied to, if I can write like this, and e to the minus z square n naught z. So, again I can write e to the minus z square, this n naught will cancel out, then I can write this in this form, that is half 2 by root pi, this is the form, that is ERFC of half root EB by n naught. Now, the probability of error when symbol 1 is sent and detected as 0, again I will get, after calculation same type, again I will get the same expression. Now, I will get the average of the probability of error, that is P equal to P naught plus P1 by 2, again I will get that P equal to half ERFC of half root EB by n naught, or P equal to half ERFC of, if I will take this inside, then root EB by 4 n naught. These are the calculation of probability of error for ASK. These are the reference books. You can find out everything in these books, and this is the all about the ASK, and in next class we will see the FSK. Thank you very much.